All right, thanks for coming, everyone. I hope you all had a good weekend. So right now we're right in the middle of our discussion of properties of seawater. In particular, on Friday we talked about some of the physical properties of seawater. We'll finish that up today and start talking about chemical properties of seawater as well. So on Friday we started talking about chemical bonding. In particular, that there are different types of chemical bonds. There are covalent bonds where electrons are being shared between atoms. And in fact, water molecules are an example of covalent bonding. The hydrogens and the oxygens sharing electrons to form a bond, and those are very strong bonds. You can also have ionic bonds where you have cations and anions in proximity to each other. They're going to feel an attraction because, of course, opposite charges attract. That can be quite strong also. And then finally, we have hydrogen bonding, which is sort of a weak form of ionic bonding where, for instance, a water molecule, the hydrogen atoms have a slight leftover positive charge. They're bonded to oxygen sharing electrons, but they sort of have fewer than one electron on average. They have one electron in their nucleus and therefore are left over with a little bit of extra positive charge, which will tend to attract any slight negative charges that are sitting around. Okay? And in fact, it's quite good at this and will form these hydrogen bonds, which are weaker than covalent and normal ionic bonds, but are strong enough that they can actually substantially affect properties of water. Okay? In particular, these contribute to the condensability of water molecules to make liquids and to make an ice, each oxygen being able to attract a couple of hydrogens from different water molecules nearby, and each hydrogen in a water molecule being able to attract and form hydrogen bonds with a couple of oxygen atoms from water molecules nearby. This doesn't necessarily have to be the case that hydrogen bonds are formed between hydrogen and oxygen. This could easily be an anion, for instance, a chloride. Okay? And this could easily be a cation like sodium. So in part because of this hydrogen bonding ability, and also partly because water is just a very low mass molecule, water, particularly in its liquid form, tends to have a very high heat capacity. It has a very high heat capacity relative to normal things that we would think of from everyday life, like stone, like organic liquids, gasoline, particularly relative to things like metals, which have very low heat capacities, relatively speaking. And about the only thing with a higher heat capacity is ammonia. And in fact, ammonia is another hydrogen bonding substance, so it actually is part of a class with water. Okay? Hydrogen bonding of small molecules is associated with a high heat capacity. And that's not the only thing that hydrogen bonding affects in water. Of course, there's also phase changes, okay, particularly going from solid to liquid, melting, and going from liquid to the gas phase or to a vapor phase, which is boiling or evaporation, depending on the conditions at which it's occurring. And both of these require energy to happen. To go from solid to liquid requires an input of energy. To go from liquid to vapor also requires an input of energy, actually in that case a lot of energy. So that if we were to plot for a sample of 1 gram of ice, how much energy we have to put into it to raise its temperature by various amounts, we would get a plot that looks something like this, where if we take ice at minus 30 degrees, 1 gram of it, and we start adding heat to it, it's going to warm up, okay, because the heat capacity of ice is about 1/2 of a calorie per gram per degree Celsius, or about 2 joules per gram per degree Celsius. And so when we've added something like 15 calories or 60 joules of energy to a gram of ice, it's raised its temperature up to a 0 degrees, at which point, of course, pure ice begins to melt. While it's melting, the energy that you're putting into the ice is not going to increasing its temperature anymore. Instead, the ice just sits there at 0 degrees Celsius and melts to form liquid. And it's only when all of the ice is gone and you've completely formed a liquid that the temperature can start going up again. Okay? So what we have in this instance, over this interval, we're adding energy, we're adding heat, but we're not changing the temperature. And so this is an example of latent heat. Okay, there's heat going into the substance, but the temperature is not changing. Instead, it's going into rearranging or breaking chemical bonds. Okay, so it's latent. Okay, it's not obvious just by measuring the temperature what you've done to the heat, but it's certainly going into that substance. Okay. Once we've completely formed liquid, if we continue to add energy, the temperature starts to go up again. Okay, just like tap water on the stove. Here, the rate at which the temperature goes up with the addition of energy is a little bit lower than for ice because the heat capacity of liquid water is very high. It's higher than ice. And the temperature goes up until we reach 100 degrees Celsius, at which point liquid water begins to boil. Okay, again, analogous to putting tap water on the stove to make spaghetti or whatever. It warms up. Eventually, it starts to boil. And once it starts boiling, temperature stops changing again. Okay, we have encountered another interval where there's latent heat. And in this case, it's the latent heat of vaporization or the latent heat of boiling. At 100 degrees C, it's going to stay at that temperature until we've added enough heat to the system to break all those leftover hydrogen bonds and make a vapor, completely converted into a vapor. Okay? And that turns out to be a lot of heat. It takes a tremendous amount of heat to evaporate or to boil, to vaporize water. Okay? So that's actually kind of the, most of the heat on this figure. To take ice from minus 30 degrees up above 100 degrees Celsius is actually just at that point of boiling the water at 100 degrees Celsius. And then, of course, once it's completely boiled to steam, the steam can be at whatever temperature you want. It can get hotter than that. Okay, you've all had experience with this. Okay, when you cook spaghetti or anything else where you boil water on the stove, that water will heat up until it starts boiling, and then it will start boiling. And, of course, the stove is still on if it's boiling. As soon as you turn it off, it stops boiling. As long as that water is boiling, you're converting liquid water to water vapor, and it stays at 100 degrees Celsius. Okay, you're adding heat, but you're not changing the temperature. Instead, you're driving a phase change from liquid to vapor. And this is one of the reasons why boiling water is really useful. It's an easy way to make something that is at a stable temperature, 100 degrees Celsius. Okay, and, of course, a little water will stay at that temperature for a really long time because you have to dump a lot of energy into it in order to boil it away. You can think of putting your spaghetti water on the stove. It takes 5-10 minutes to start boiling. Then, I don't know if this has ever happened to you. It certainly happened to me once or twice. You get involved in a TV show or football game or something. You kind of forget that the water's boiling for an hour or two, and you come back and there's like a tiny little bit left boiling in the bottom, and you all of us, turn it off really quickly, and you're like, "Ooh, that was close. I almost roasted my pot." It takes a long time to boil away all that water compared to how long it takes to make it boil in the first place. And that's because of all the energy that's required to actually convert liquid water to vapor phase water. So the distinction to be made here is that there's energy which goes to raise the temperature, and that occurs when you have one phase present. So when you have liquid water, you add heat to it, you raise its temperature a little bit. When you're changing the phase, when you're going from solid to liquid or from liquid to vapor, adding heat to a pure substance actually doesn't change its temperature. You're just changing the phase. Okay? So we're going to make a distinction between sensible heat, where adding heat raises the temperature, and latent heat, where adding heat doesn't change the temperature or doesn't change it very much. Instead, it drives a phase change. Okay, the energy is still being absorbed, but it's not going to an increase in the temperature. Okay, so we're going to be interested, much like we were in understanding how circulation works deep in the Earth, the fact that convection is involved in plate tectonics. Of course, convection also happens in the oceans, where you have warm water at depth or less dense water for whatever reason. It's going to tend to rise towards the surface, and particularly for the oceans, where you have very dense water at the surface, it's going to tend to want to sink. And one of the important controls in the density of water is its temperature. In general, liquid water becomes more dense the colder it gets. Now, liquid water is actually a little bit weird, and water in general is quite weird among typical substances because this tendency to get denser as it chills is not continuous. If you take liquid water at high temperature, let's say starting near the boiling point 100 degrees Celsius, and you cool it down, it gets denser and denser. Okay, so the same mass of water is getting smaller and smaller in its volume, okay, but it actually kind of levels out and reaches a maximum density just above its freezing temperature at about 4 degrees Celsius. kind of a refrigerator temperature. And it's almost level, but actually slightly decreases to 0 degrees Celsius. So if you cool water very close to its freezing point, pure water, it actually starts to expand a little bit. And then the weirdest thing of all is that if you actually start to freeze that water, its density drops a lot, 8 or 9%, something like that. Okay. You already know this. Ice floats, right? Ice is less dense than water. But this is actually really, really unusual for any substance. There are very few materials that expand when you freeze them. Almost everything else will become more dense when you freeze it. Water is a little bit of an exception here. Now, it turns out that from the perspective of oceanography, this business about reaching a maximum density before the freezing temperature turns out not to be the case for salt water. If you mix a little bit of salt into fresh water, it actually changes its properties in such a way that it continues to become denser until it reaches the freezing temperature. Okay, so seawater actually, its maximum density is right before it starts to freeze. But it's still the case that the ice that forms from that water, even if it's a little salty, if the water is a little salty, the ice that forms is much less dense. Okay, icebergs float. So why does this happen? This is a weird property. And it turns out, like many of the other weird properties of water, to stem from its hydrogen bonding. Okay, the density of solid water, of ice, at least the normal form we encounter in the ocean, is about 8% less than liquid water at the freezing temperature. Okay? And this has to do with the fact that the water molecules in ice are essentially locked into a lattice. They're making the maximum possible number of hydrogen bonds. Okay, which is great, right? If something makes lots of bonds, that's sort of the minimum energy configuration for it. But it turns out that in order to make all those bonds, they kind of have to spread out a little bit, okay? Because the angles at which these bonds form aren't really conducive to the formation of a really compact solid. Okay, and the geometry of the water molecule actually changes a little bit in the process. Okay, so the net result is that ice is less dense than liquid. Ice floats. This turns out to be really important for understanding how the ocean behaves. Actually be kind of annoying if ice sank, because then the bottom of the ocean might freeze, and well, that would be no good. Okay, so what's the analogy for this? I'm going to argue that water molecules are very much like undergraduates at UCLA. And here's why. When you guys are sort of at your maximum energy level, like on a Saturday afternoon when it's a nice day, you're out playing frisbee, you're going shopping, you're taking the bus to downtown to see the museums, you're all spread out, right? So when you guys are at your maximum energy levels, you're really not very dense. UCLA expands to cover a great range of Los Angeles. Okay? When you're at your lowest energy level, okay, you're asleep probably in your dorm room, right? So you're in buildings, and you're mostly on UCLA's campus, or if you're not a resident student, you're sleeping at home, okay? And you're obviously taking up much less space. You're not running around everywhere. But your densest packing is actually at an intermediate energy level, and that's when you're at lecture, right? Because now you're all crammed into this one little room. And you're not as energetic as on a Saturday afternoon when you're playing frisbee and shopping. But hopefully you're not quite as catatonic as when you're asleep, okay? And yet here you're at your maximum density. Okay, so just like water, undergrads at UCLA reach their maximum density at an intermediate energy level, in the intermediate phase. Okay, in the liquid phase in the case of water, in the lecture phase in the case of students. Okay, so this property that water generally becomes more dense when it's cooler, but less dense when it finally freezes, has really important repercussions for convection in the ocean, okay? And this turns out to be the driving mechanism really for flow of water in the deep ocean. So this is just a movie I cribbed off of YouTube, a cup of water. This is an ice cube with some green food coloring added. Okay, so we're seeing all of these properties of water kind of in this one little video. The ice is floating. It's less dense, even though it's the coldest thing in the system. It's chilling the water around it, and of course it's melting as it comes into thermal equilibrium with the water around it. The liquid water at cold temperatures is, of course, more dense than the surrounding room temperature water, and so it tends to sink towards the bottom. So this is a case where We're creating cold water at the surface by adding ice, okay, which floats, and that cold water is tending to sink as it becomes more dense. Okay. So where would we expect this process to be happening in the ocean, say? Yeah, near the poles, right? Maybe making sea ice or something like that, or it's just cold weather at the surface. You're making cold water at the surface that can sink. And this actually turns out to be, you can see in this video, we're fairly quickly filling up the bottom of this little cup with green water, which was just at the surface. That's why it's green. Somehow got close to this ice cube and was able to diffuse in some of the food coloring from the ice cube. And now it's kind of filled up the bottom half of that cup. Okay, so most of the water now in the bottom of this cup is water that used to be near the surface, very close to this one ice cube. And actually, that's a pretty good analogy for our oceans. It turns out that most of the water in the deeper parts of the ocean used to be near the surface, right near places where ice is forming, okay? Right near the poles, because that's where you make the densest water, at the Earth's surface. Now, I haven't told you everything you need to know to understand this, because it turns out that salt is important, okay? But temperature is critical for understanding why the ocean has temperatures and flow conditions that it does. And of course, convection is not just important for plate tectonics. It's not just important for understanding where water in the ocean comes from, but of course it's important for the atmosphere. This is just a little time sequence for a hurricane in the Atlantic Ocean, I think. Okay, and you can see convection happening in the atmosphere. In terms of the rate of convection, actually atmosphere is the fastest convector of all. You can see these little thunderstorms popping up along the edge of the hurricane, and the whole hurricane itself turns out to be driven by convection, by the rising of warm air, in the case of a hurricane, warm, moist air, and the sinking of cooler air around it. Okay, so are there any questions about physical properties of water? Yes? The question is, does salt in the water make it less dense? It's the other way around. So salt is going to turn out to make water denser. It makes water denser, and if you could put salt into ice, it would make the ice denser, but ice actually tends not to like to have salt in it, so it tends to be fresh. We're going to get there in a few slides. It makes it a little bit denser, because there's not that much salt in water, at least not normal seawater. Okay, so that was an excellent segue to the chemical properties of seawater. So we've already learned what water is, right? It's a thing that you make by sticking one oxygen atom into covalent bonds with two hydrogen atoms. But that's not the only thing that's in seawater. In fact, pretty much the whole periodic table is in seawater in some concentration, but it turns out that some things are much more important than others. And it's important to understand a little bit about why that is. Okay, so big picture here is that water is almost a universal solvent. Water is very good at dissolving lots of different things. Not everything, but lots of things. Okay? And this, again, has to do with hydrogen bonding, the fact that water has these leftover positive and negative charges on its ends. So it can kind of pretend like it's an ion to some extent. It has a charged side in the negative sense, and it has a charged side in the positive direction. So regardless of what kind of charge you throw in it, it's going to be able to form kind of a weak ionic interaction with it, because it's going to have a side of the water molecule that's the opposite charge to anything that tries to come into contact with it. So for instance, if we have salt, which is what these little blue and green balls are supposed to indicate, the crystal structure of sodium chloride, okay, water molecules can actually come in, and if it's a negatively charged ion like chloride, the positively charged ends can actually come in and be attracted to it, surround that anion, and bring it into solution. If it's positively charged, like a sodium atom, the oxygen ends of the water molecule can come in and interact with it, solvate it, and bring it up into solution. So what we're seeing here is actually a snapshot from a model. So this is a model where well, not me, but a model where sodium chloride is actually allowed to dissolve into a model water molecule which has a certain charge associated with it. So this is a computer model. And you can see that the water is actually pulling off the sodium and the chloride from this crystal structure. And water can do this pretty much to anything that likes to form charges. So sodium, chloride, okay, things in the sodium column of the periodic table, things in the chloride column of the periodic table. Things that are on the left side of the periodic table tend to form cations. things that are on the right of the periodic table tend to form anions. To the extent that they form those charged particles, water will tend to some extent to want to dissolve them. And of course, if you have a molecule that's actually like water in the sense that it has a positively charged end and a negatively charged end, water is also going to tend to be able to dissolve that. So ammonia, for instance, okay, has a positively charged hydrogen atoms, has negatively charged nitrogen atoms, and the water can dissolve that. About the only stuff that water doesn't dissolve well, that's not quite true, but the most important from the point of view of oceanography in any biology class is that water doesn't really do a very good job of dissolving things like oils, like hydrocarbons, that don't have any charges, that don't form ions very easily, and that don't really have positive and negatively charged ends to them. Okay, so things like oils fall into that category. Water doesn't really have much of a grip on them. It's got a hard time dissolving them, and so they tend not to dissolve. They tend to stay separated. This turns out to be really important from the point of view of biology, because that's basically what keeps us from falling apart into a puddle of goo. Okay, the cells in our bodies and in pretty much every organism actually have two components. The molecules that make up our cell membranes, they have a part that is chargeable or polar, that attracts water, but they also have a big part that isn't, that's not polar, that doesn't have charges, that tends to stick to other molecules that have that same property and not be dissolved in water. Okay? And it's the formation of bonds between those water-phobic parts of the molecule and then the outside parts being water-philic that actually makes a cell membrane that can keep water on the outside separate from the cell contents on the inside. Okay? And if you throw some molecule into contact with a cell that can dissolve both of those things, like soap, that's really bad news for cell membranes. And in general, it's bad news for anything that has exposed, not waterproof outer covering. So salt is bad news for lots of bugs, for instance. You can kill bugs just by pouring soap on them, essentially because you start dissolving their insides. Okay. So water is great at dissolving stuff, especially stuff that likes to form charges, stuff that's polar, has positive and negative ends. This is particularly true for things like sodium and chloride that form plus and minus 1 charges or plus and minus 2 charges as ions. Okay? And so this is just put together. It doesn't really have much scientific significance as this particular arrangement, but the basic idea here is that a negatively charged anion is going to tend to attract the positively charged cations, positively charged hydrogens on water molecules, and a positively charged cation is going to tend to attract the negatively charged oxygen ends of water molecules. Okay? And the ratio of water molecules to sodium and chloride here is actually not nearly high enough to be seawater. This is actually like a completely saturated salt solution, but it gives you an idea. So it shouldn't be a surprise to us that if we have water in nature and we have things like sodium and chloride and lots of other things in rocks, that the ocean actually dissolves these things and becomes salty over time. And so the ocean is saline. It has dissolved salts. And for the most part, those dissolved salts are actually sodium and chloride. Those are by far the most abundant salts dissolved in seawater. They are dissolved, so they occur as ions, sodium plus and chloride minus. There aren't actually salt crystals or sodium chloride molecules in seawater, at least they're very rare. In order to make them form molecules or to form crystals, you actually have to evaporate seawater. In the case of sodium chloride, you actually have to remove something like 90% of the water for the salt to saturate and start crystallizing. There are a few places along the edges of the oceans mostly where that happens. In some cases, we induce that to happen because, of course, salt has some value. And so, for instance, at the south end of San Francisco Bay, there are a number of salt works. That's what's showing up as kind of purplish in this picture. The magenta colors are actually salt evaporation ponds at the south end of the San Francisco Bay, just a little ways north of us. And you can actually see areas where the salt is evaporated and is being piled up. That's what that white stuff is. So the purpley color there, by the way, is not the salt itself. Salt is white. The purpley color is strains of bacteria, halobacteria, that actually do photosynthesis and love to live in really salty water. Okay? And the color is actually reflecting their photosynthetic ability, or pigments inside the organisms. Oh. So this is an exception. In these places, the salinity of the water is probably up above 10% or something like that, 20, 30%. Normal seawater is actually usually in a very narrow range in its salinity, with about 3.5% dissolved material. And in fact, it varies relatively little from place to place for most of the ocean. Salinity is fairly consistent. Well, it's only 3.5%, but of course the ocean's a big thing. So if you evaporate the entire ocean, that's enough to actually generate something like an 80-meter thick salt layer over the whole planet, which is plenty for French fries. So where does the dissolved stuff come from? A couple places. And this is actually not that different from our discussion of where does water come from. Kind of similar. So a lot of the dissolved material in the oceans, a lot of the salinity comes from just weathering of rocks on land, or hot water flowing through rocks under the seafloor and dissolving materials out of the minerals in those rocks. In order to find a picture of something where you could actually kind of see dissolved stuff, it's actually a little hard. But this is a picture of the Rio Tinto in Spain. It's a place where there's been mining, metals mining, for hundreds, maybe even thousands of years. It turns out that when the mine tailings, the leftovers from this mining activity, reacts with the air and water, it makes sulfuric acid, which is really good at dissolving stuff. And so it actually has enough dissolved stuff in it that the water kind of turns this funky red color. This is where most of the things like sodium, calcium, magnesium come from in the ocean. But there are some things that can't really be explained that way, particularly things that like to go into the gas phase rather than forming rocks. So the water itself, we talked about being trapped in the earth from the original meteorites that formed our planet and then degassed through volcanic activity. And there are other materials that are dissolved in ocean water that come out probably the same way. Carbon dioxide, hydrogen chloride or hydrochloric acid, nitrogen, hydrogen sulfide, a number of other gases, SO2, depending on what kind of volcano it is. And so stuff dissolves in the ocean by the reaction of water with rock, or it can actually be degassed to the atmosphere by volcanic activity and then dissolved in the ocean after that, or dissolved in rainwater that then falls in the ocean. So if we look at what that dissolved material is, and for the moment we're going to leave aside some of the gases, which are rarer in seawater but turn out to be important later, and only look at those things that can form salts. Again, about 3.5% of seawater is dissolved material. And most of that dissolved material, more than 80% of it, is sodium and chlorine, sodium and chloride. So the saltiness of seawater is fairly simple. It's fairly close to the table salt you have. There are some other things that are important. There's sulfate, there's magnesium, there's calcium. Remember we talked about calcareous oozes being formed from calcium carbonate skeletons or shells. Okay, so there's calcium in seawater that can go into those shells, potassium, and so on and so forth. But really just a handful of things can explain something like 99% of the dissolved material in seawater. And the interesting thing is, certainly for all of these things, chloride, sodium, calcium, magnesium, potassium, if you go to one part of the ocean that's a little saltier or another part of the ocean that's a little bit fresher, even to one of those ponds in the San Francisco Bay where the salt is almost ready to start coming out but hasn't quite done so yet, many of these things you'll typically find occur in constant ratios to each other. Okay, so it doesn't matter if the water's a little saltier or a little fresher. The ratio of chloride to sodium, or the ratio of sodium to sulfate, or the ratio of calcium to magnesium is typically constant, okay, or very close to being constant. So we can call that sort of a law of constant proportionality. Even though the salinity of seawater varies a little bit from place to place, the major dissolved constituents in seawater occur in constant relative proportion to each other. What this tells us, or at least gives us some reason to believe that seawater is actually stirred. It's mixed. So it may be that one stream that's draining into the ocean has lots of sulfate in it, lots of dissolved sulfate and lots of dissolved magnesium, and another stream has lots of dissolved sodium and chloride. Okay, so locally, where that stream enters the ocean, there may be a little bit more of one thing or another, but the ocean as a whole kind of circulates and mixes away those differences in what's being put into it. So this is one implication that seawater, the oceans, are actually dynamic. Okay? Their concentration, concentration ratios of the major dissolved constituents of that water are similar from one place to another. We can take that idea a little bit further and maybe make it even more sensible by bringing up the idea of a chemical residence time. So you can think of this as being for whatever you're interested in. Sodium chloride, the water molecules themselves, some biological molecule, or a pollution molecule. How long, on average, does one particle of that stuff spend in the ocean before it falls out? Or we can think of it in terms of how quickly are we adding it to the ocean, or is it being added to the ocean naturally relative to how much is already there? Okay, so this gives us a sense of rate of change or consistency of the material in the ocean. Okay, we can calculate a residence time by taking the amount of a particular element or molecule in the ocean and dividing it by the rate at which it's being either added or removed. We can do it either way. Sometimes we'll get different answers. If it's being added and removed at the same rate, we'll get the same answer both ways, and we can say it's at steady state. Okay, so this is a little weird. I know this is something that earth scientists really like to do. We like to calculate residence times for things or average lifetimes. A lot of other sciences don't do it quite as often, so let's go through an example. Let's take chlorine, which remember is the most abundant dissolved thing in seawater besides the water itself. There's something like 2% chloride in seawater by mass. So every gram of seawater has about 0.02 grams of chlorine. Every kilogram of seawater has about 0.02 kilograms of chlorine. The mass of the ocean, it's big, some number times 10 to the 21st kilograms. So we can actually calculate out, assuming that that's the average concentration of chlorine and that's the mass of the ocean, how much chlorine there is in the ocean. So this is 0.02. This is a scientific notation problem because this guy's in scientific notation, so we want to make this scientific notation so we can move the decimal place here. So this is in scientific notation what? 2 times 10 to the negative 2, because it's less than 1. And we're going to multiply that by 1.4 times 10 to the 21st. So how do we do that? We multiply the coefficients. So what's 2 times 1.4? 2.8, or about 3. And then we add the exponents. So we have 10 to the minus 2 and 10 to the 21st. So we end up with 3 times 10 to the 21 minus 2. 3 times 10 to the 19. Yes. So we end up with a reservoir of 3 times 10 to the 19 kilograms of chlorine in the ocean. If we go around to all the world's major rivers and we just figure out how much chlorine is in this river water and how much water is that river dumping into the ocean, we can come up with a rough rate of addition of chlorine to the ocean of something like 2.2 times 10 to the 11 kilograms per year. The amount of chlorine that's in the ocean is 3 times 10 to the 19 kilograms per year. So 3 divided by 2 is what? It's about 1 point something, 1.4, something like that. And then 10 to the 19th divided by 10 to the 11th. Subtract the exponents when you're dividing. So 19 minus 11, 8. So we have an answer that's something like 1.3, 1.4 times 10 to the 8th years. That's a long time. That's 100 and some odd million years. Okay? So the residence time for chloride in ocean water is really, really long. Okay? Oops. Over 100 million years. Which means that there's a lot of chlorine in the ocean relative to how quickly it's being added or removed. Once a chlorine atom gets dissolved in seawater, it tends to stay associated with the ocean for a really long time. Now, I mentioned that we can calculate this by using the rate at which the element's being added, or we can calculate it using the rate at which the element's being removed. In the case of the calculation we just did, we worked with the rate at which it was being added. In many cases, that's an easier number to get. We can assume that the rate at which it's being removed is the same, in which case the concentration isn't changing over time. You're adding and removing stuff at the same rate. So unless the ocean changes in size, its concentration is not going to change. And so that is an assumption of kind of a long-range steady state. And as far as we can tell, looking at things like salt deposits, and in a few cases we actually get trapped little droplets of seawater associated with salt deposits and other things, it looks like the ocean, in terms of the major dissolved elements, has been relatively consistent in its composition for a long period of time. Okay, at least 100 million years, probably more than that. So we can make a steady state assumption that seawater hasn't strongly changed over the past several hundred million years. That's not strictly going to be true. It turns out there is evidence that some things have varied, like the calcium to magnesium ratio in the ocean. But for the purposes of this class, we can treat this as being close enough for our purposes. And the basic idea then is that what goes in should eventually come out. It's not like the ocean is a dead end for something like sodium or chloride. Rivers are bringing it in, but it appears to be going out at roughly the same rate. Okay. Otherwise, given what we just calculated for the residence time of chloride in seawater, if we project back 130 million years and assume that it's not going anywhere, that would imply that the oceans were fresh 100 million years ago, and there's no evidence that that's true. In fact, there's plenty of evidence that it was salty 100 million years ago. So it must be going somewhere. And where it goes actually depends on what you're talking about. Some things get bound up in seafloor sediments. Calcium. Okay, it goes to make calcium carbonate, which many organisms use to make their shells. It goes into coral reefs, falls out to the bottom, at least in parts of the ocean that are above the calcite compensation depth, and gets removed from the oceans that way. Okay? Sodium chloride can go to form salt. If we look at residence times for the major things in seawater, like chlorine and sodium, they're by and large very big numbers. We calculated the residence time of chlorine is something like 100 million years. Sodium, you actually get a pretty similar number, 60 or 70 million years. Okay? Well, that's not true of everything in the ocean. There are some things that actually seem to be getting added and removed much faster relative to how much is in the ocean. And an example of that might be silicon, which has a residence time in the ocean of something like 20,000 years. Water itself has a residence time of a few thousand years in the ocean, which seems a little weird, right? Okay, the oceans have been there, pretty good evidence the oceans have been there for billions of years, and yet the residence time of water in the ocean is only 4,000 years. Well, we actually kind of know what happens, right? How does the water get out of the ocean? Yeah, it evaporates, right? You make clouds. What happens to the water after it evaporates? Its fate ultimately is to rain out somewhere. It gets into the ground, it gets into a river, or it falls directly in the ocean. Somehow it gets back to the ocean pretty quickly. Okay, but its residence time is pretty fast, pretty short period of time, because it evaporates pretty easily and falls out pretty easily. And there are some things that have really short lifetimes, iron among them, tens of years, hundreds of years. I know it doesn't seem like a very long time, but relative to something like chlorine with 100 million year residence time, that's pretty short. Okay, this turns out to not be just a chart to remember like baseball statistics or something. It actually turns out to be really interesting from the point of view of figuring out how the ocean works as a chemical engine. And this comes from the idea that, as far as we can tell, the oldest water masses in the ocean are a little more than 1,000 years old, something like 1,600 years old. And in this instance, what I mean by age, or old, is how long has it been since that part of the ocean, since some parcel of water in the ocean was last up near the surface? And it turns out that number is something on the order of 1,000 years. And actually, the oldest water you find in the ocean is mostly found in the deep parts of the Pacific. So you can imagine that the ocean is stirring itself up. If everything's making it up to the surface every 1,000 years or so, okay, then that's kind of the time scale for overturn for mixing of the ocean. So for an element like chlorine or sodium, which has a residence time of millions or tens of millions or hundreds of millions of years, it's gone around and around and around and around hundreds or thousands of times. It's been stirred thoroughly, okay, like cake batter or something. And so it shouldn't be a surprise at all that these things occur in constant proportions to each other. They're in the water for so long before they're added or subtracted that they're just completely stirred up. Okay? And we call these elements conservative. Okay? They occur in constant proportion to each other. They seem to stay in the ocean for a really long time. They aren't removed or added easily. And so they're kind of a conservative quantity of seawater. This includes pretty much all of the things I showed you on that previous box diagram. All of the major dissolved elements in seawater fall into this category, including chloride, including sodium, including magnesium, including potassium, including sulfate, including calcium. But not everything falls in that category. Okay? In particular, something like iron, and it turns out actually silicon too, at least in some parts of the ocean, is being added or subtracted more quickly than the ocean is mixing itself. So what should you expect to happen in that instance? What if I'm adding iron, let's say where Rio Tinto, that weird orange river in Spain, comes into the North Atlantic Ocean. It may actually go into the Mediterranean, I've now forgotten, but it comes in somewhere near there. Okay, and it's dumping all this iron into the ocean. Okay? Iron has a pretty short residence time in the ocean. So what would you expect to happen to that iron as you get away from a really concentrated source of it? What would you expect its concentration to do? If you're away from the part of the ocean where it's being added, and it's being removed on a time scale of a couple hundred years, and it takes 1,000 years for the ocean to mix itself. Yeah, it's going to get removed. So if you go away from the source of iron to the ocean, the iron concentration in seawater is going to drop. And it's going to actually drop by a lot. It turns out that iron's not very soluble in seawater for one thing, and it's an important nutrient for another thing. So organisms are trying to pull it out of the seawater all the time. And there are lots of elements that turn out to have this property. Some of them do so because they're not very soluble in seawater. Iron is in this category, aluminum, titanium. Some of the elements that form really strongly charged cations tend to fall into this category. Some things have short lifetimes because biology wants them. They're nutrients. Okay? So think of oxygen, which is used by organisms like us that do respiration for a living. Iron is a critical nutrient, so is phosphorus, so are certain forms of nitrogen. Carbon dioxide is a nutrient for plants. Silicon isn't something that we need in our diet necessarily very much, but we just learned about these organisms, diatoms and radiolaria, that use silicon to make their shells. So for them, they really need that in seawater. And so organisms are actively involved in either adding or subtracting these materials from seawater. They can do so fast enough that they actually change the balance of it in the ocean, change its concentration from place to place. And then there are also chemicals that are either being created or destroyed by human activity. And so one example of something with a short residence time whose concentration in seawater varies from place to place is freon, CFCs, chlorofluorocarbons. These are wonderful molecules. These are life-saving molecules that were created, essentially, in particular this one, CFC11, to improve the safety of refrigerators. Okay? This stuff is basically non-flammable. Okay? It won't blow up. And before these things came along, when people wanted to make refrigerators, they wanted things that could get down below freezing without freezing. So you can't use water to make your refrigerator. They had to use, as a working gas, something like ammonia. And ammonia is pretty soluble, and it's also pretty poisonous. Okay? And so, not too uncommon for refrigerators to explode, okay, or cause fires. When these things came along, these chlorofluorocarbons, they don't cause fires. It was great. It was wonderful. And you could make a refrigerator that would work beautifully. The problem is, those molecules are so non-flammable that they're basically indestructible. their lifetime in the atmosphere is of the order of 100 years. So when they escaped from a refrigerator because it had a leak or somebody's air conditioning unit, they would just accumulate in the atmosphere, and they can actually get up into the stratosphere where they could destroy ozone, which turns out to be a bad thing. Okay? So in the 90s, we actually started phasing these molecules out. They were invented and became widespread in the 50s. Their production went up as more and more people were able to buy refrigerators and air conditioners. We realized that they were harming the environment, and we started phasing them out. So if you look at the abundance of this stuff in the atmosphere as a function of time, it starts out very close to zero. There's very little of this stuff naturally present in the atmosphere. It's basically entirely man-made. Then it rises very quickly because it's really useful stuff. We realize it's causing problems, and we basically outlaw it or phase it out, and its concentration in the atmosphere slowly starts to decrease. Okay, so we have this very well-known history of the concentration of this molecule in the atmosphere. If we look in seawater, we can actually see the consequences of this rise in concentration in the atmosphere. If we look in the total inventory, so we're averaging all the way from the bottom of the ocean to the surface at various parts of the ocean, the highest concentrations of chlorofluorocarbons are found in a few places in the ocean, in particular in the North Atlantic, off the coast of Greenland and Europe, and to a certain extent also in the Southern Ocean off the coast of Antarctica. Okay. For Wednesday, I want you to think about why. Why is it that this stuff, which has only been produced in the last 40 or 50 years, is far more common in this part of the ocean than, say, this part of the ocean? All right, I'll see you on Wednesday.